In Module 7 of Chapter 20, we're going to take a closer look at the so-called risk-neutral process. We've already seen risk-neutral pricing in the context of the binomial tree, or the binomial lattice, where we talked about the risk-neutral probability P star. And we also saw how the risk-neutral pricing versus risk-averse pricing can be embedded in the utility theory from an earlier chapter. So in this chapter, we're going to look at stochastic processes, and in particular, risk-neutral processes. From Chapter 11, we have P star, as I just mentioned, and under P star, we saw that the expected value of the future stock price is equal to the forward price of that stock. So under P star, we can derive that over any interval of time, from time t to time t plus h, that the expected value of the stock price at time t plus h is in fact the forward value of the stock price from time t, the forward value at time t plus h. And this comes from the formula in that earlier chapter, where we saw that when we took the present value of the expected stock price, we got this term you would recognize as the prepaid forward of the stock. And so the present value of the expected stock price is the prepaid forward. If I multiply by e to the RH, I get the forward itself. Now we're going to investigate the same idea with processes next. So imagine that we have a price process for a stock. Alpha is again the expected return in the real world. It's the real world return. And then delta is the continuous dividend rate. Sigma is the annual volatility. All the usual notation, except here we're now explicitly accommodating a continuous dividend flow of delta. So that the implication of this equation is that this tells you the change in the stock price. So alpha minus delta is the capital gain or loss. Remember, these equations tell you what happens to the price of, say, a single share of stock. DS is the change in price of a single share of stock. And therefore, it will only reflect the capital gain or loss in a share of stock. In addition, an investor has a dividend payment of delta. So for a very small interval time, delta S is going to be the dividend. So while an investor has a capital gain of alpha minus delta times S, the investor will get delta times S as a dividend, and then altogether the investor gets a total return of alpha. So the alpha total return is still the same. It's just that in this equation it's only the capital gain component that's reflected, because the dividends are now assumed to be flowing out of the stock to the investor in cash, not reinvested in stock, because these equations represent the change in price of a unit of stock. They don't reflect the change in price of an account in which you add one stock and reinvest dividends. It's very important that you understand the difference in these two notions. This is an equation that tells you if you buy 1 unit of stock, what is the process that defines the price change of that single share of stock. If I put a single share of stock in an account and I reinvest dividends in additional stock, the process for that account will not have the minus delta term, because now the total value of the account will grow with alpha because dividends are going back in. Okay. So the risk-neutral version of this process is obtained by subtracting the risk premium from the drift. So I have a drift which gives me the risky capital gain and loss. And by removing the risk premium, I end up with the risk neutral. And this is, you'll note that this is in fact the drift term that we used in our earlier binomial lattices, where we assumed over the period of h we had a drift of r minus delta h, and then we had a volatility term of plus or minus sigma square root of h. Well, this is, and the reason for that is in those binomial lattices we were modeling in a risk-neutral environment. So here we see how that comes about. We take the original process and subtract the risk premium. And notice that we have a new dz. This dz will also be Brownian motion, but it's a different Brownian motion than the original one, and we'll see how that came about. We'll see how one, in fact, goes from the original equation from this, because it seems a little mysterious that we've just arbitrarily reduced the drift term and then said, well, okay, we have a new dz. And that seems to be a little mysterious how exactly that happens, and we need to investigate that further, and we'll do that next. And we'll find that the conclusion will be that, in fact, the new dz has a term in it that we've subtracted from the drift, but then we change the probabilities on that dz to make it Brownian motion. And this is very similar to what happens on a binomial lattice, where in the real world we might have a probability p, but to make things risk neutral we use probability p star. So mathematically this is what happens. We have the original process here defined in terms of alpha and delta. In order for us to subtract the risk premium from the drift, we have to put it someplace, otherwise we don't have equality, so we're going to stick it into the term, and you see what happened. What we need to now convince ourselves, so what we did was we changed the original sigma dz to be sigma times, we now have a new volatility term that's the old dz plus the Sharpe ratio times dt. So this old dz term, we've stuck a drift in it. And the question becomes, can I make this into a new Brownian motion? Can I take a Brownian motion with a drift? So this looks like an arithmetic Brownian motion, doesn't it? Is there some way of taking arithmetic Brownian motion and changing the probability structures of those various paths so that with the new probabilities I get a traditional Brownian motion without the drift? Namely, and I'll call that dz star.